Welcome to Fear the Engineer, where I explain engineering topics better than your professor. In the last video, we learned all the concepts and formulas of uniform circular motion. Now, we'll put our knowledge to the test with some practice problems. First, let's review the formulas. Here's a particle traveling around a circle. The variable r is the distance between the particle and the center of the circle. The variable theta is the particle's angle compared to some reference, like the horizontal axis. The arc length s tells you the distance along the circle between the particle and the reference. It equals r times theta in radians. You can also find the arc length between two angular positions. The angular velocity is the rate of change of theta, and it is constant because we have uniform motion. The particle revolves around with a constant speed, so its angle changes at a constant speed. Omega has magnitude and direction. You can find omega by looking at the slope of the theta versus time graph, or you can use these two formulas to find its magnitude. The first requires knowing the period of the particle's motion. The second requires knowing the angular position at two different times. For the direction, we write omega as positive if it is counterclockwise. Also, we can use omega to find theta. We can solve for the final theta by taking the initial theta and adding the area under the omega versus time curve. That area is often just a bunch of rectangles, with a height of omega and a width of delta time, the difference between the initial and final times. We can also use omega to find the total rotation experienced by a particle, regardless of which direction it was in. To find that total rotation, we add up all the area between the curve and the horizontal axis. You take the area above the horizontal axis and add the area below it. The particle's velocity is the rate of change of the arc length s, which is the particle's distance along the circle. That velocity always acts tangent to the curve. That's why we call it the tangential velocity. It has a magnitude and a direction. You can find tangential velocity by looking at the slope of the s versus t graph, or by multiplying r and omega. Since we have uniform motion, the angular velocity is constant, so the tangential velocity is constant. The omega times r expression only works if omega is in radians per second. You can also find the magnitude of the tangential velocity, the tangential speed. You can use these formulas. If the particle moves counterclockwise, it has a positive omega, so it has a positive velocity. Lastly, the acceleration is the derivative of the particle's velocity. It always points toward the center of the circle, so we call it the centripetal acceleration. To get its magnitude, you can use these formulas. To use them correctly, make sure you have omega in radians per second. That's it for the formulas. Here's our problem-solving strategy. We carefully read the problem, write down what they give us and what they want us to find, and start selecting formulas. Then, we plug in what we know and solve. I'll solve the problem step by step. The best way to practice is to pause the video and try the steps before I do them. Then, you can learn from your mistakes. Now, let's dive in. We'll start simple and work our way up. Here's problem 1. The distance between Jupiter and its moon Europa is 671,000 kilometers. Europa only takes 3.5 Earth days to revolve around Jupiter. Find the velocity, angular velocity, and centripetal acceleration of Europa as it travels around Jupiter. Here's a quick sketch of Europa and Jupiter. Let's list the givens and finds. The problem gives us the radius between Europa and Jupiter, and it also gives us Europa's period, t, which is 3.5 Earth days, or 84 Earth hours. We want to find Europa's velocity, angular velocity, and centripetal acceleration as it travels around Jupiter. Let's start with velocity. Tangential velocity has a magnitude and a direction. Here are the formulas we can use to find the magnitude, which is also called the tangential speed. We know the radius r and the period t, so the first formula works well. It says the tangential speed equals 2 pi r divided by the period t. Let's use it. When we plug in r and t, we get 478.72 kilometers an hour. To find the direction of the velocity, the problem must tell us, or it must provide Europa's angular position at two different times. This problem doesn't do either, so we can't determine the direction. Time to move on. We also want to find angular velocity, which has a magnitude and a direction. Here are the formulas we can use to find the magnitude, also called the angular speed. Since we know the period t, the first formula works well. Let's use it. When we plug in our period of 84 hours, we get an angular speed of 0.075 radians per hour. To find the direction, we would need more information. Lastly, we want to find Europa's centripetal acceleration, which also has a magnitude and a direction. Here are the formulas we can use to find that magnitude. We already calculated the tangential velocity, so we can use the first equation. We also calculated the angular velocity, so we can use the second one too. I chose to use the first equation. If we plug in the tangential velocity, we get a centripetal acceleration of 35.8 kilometers squared per second. For the direction, we know that the acceleration of a particle with uniform circular motion points toward the center of its path. That means the direction is always toward Jupiter. That's it for problem 1. Here's problem 2. A particle is traveling around a circle, and the graph below shows its angular position versus time. We want to determine its angular velocity at 2 seconds and at 5 seconds. Let's start by listing the givens and finds. They give us a graph of theta versus time. We want to find the angular velocity, omega, at 2 specific times. Now, let's figure out what formulas to use. Here are the formulas that help us find omega. Since we have the theta versus time graph, the top formula is a great choice. It says that angular velocity equals the slope of the theta versus time graph. So we just have to calculate the slope of our graph at 2 seconds and at 5 seconds. Let's use it. At 2 seconds, the slope is the same as the slope of that whole left portion of the graph. In this case, that slope is 0. So the angular velocity at 2 seconds is 0 radians per second. At 5 seconds, the slope is the same as the slope of the right portion of the graph. When we pick 2 points along that line and find the slope, we get negative pi over 5. So the angular velocity at 5 seconds is negative pi over 5 radians per second. Now, let's move on to the next problem. Here's problem 3. A skyscraper on the equator is 0.82 kilometers tall. One traveler stands on the skyscraper, and another one stands on a beach that's close by. We want to determine how different their speeds are. The Earth's radius is 6,400 kilometers. Let's start with a quick sketch of Earth. This is the equator. It's the perimeter of the disk in the middle of the Earth. We also know that the equator has a skyscraper somewhere along it. One traveler is standing on it, and another is on the beach next to it, which is at sea level. I'm going to draw the view of this disk from above. Now, let's list givens and finds. They gave us how far each traveler is from the center of the Earth. The traveler on the beach is 6,400 kilometers from the Earth's center, and the other traveler is an additional 0.82 kilometers further away. So we know the radius of each traveler's circular path. We also know the period of rotation, t. All stationary objects on Earth take 24 hours to complete a revolution. This applies to the traveler on the beach and the traveler on the skyscraper, since both are standing still relative to the Earth's surface. We want to find their speeds. Since the problem didn't say angular speed, we'll assume it wants the tangential speed. Let's figure out what formulas to use. Here are the formulas for tangential speed. Since we know the period t, the first one is a good choice. It says tangential speed equals 2 pi r over t. Let's use it. The traveler on the skyscraper is 6,400.82 kilometers away from the Earth's center. When we plug in t, we get 1,675.73 kilometers an hour. The traveler on the beach is 6,400 kilometers away from the Earth's center. When we plug in t, we get 1,675.52 kilometers an hour. Now that we have their tangential speeds, the last step is to find the difference between them. We get 0.21 kilometers an hour. By the way, I'd really appreciate it if you could give me some quick feedback to help me improve. The link in the description takes you to a Google survey that takes less than a minute. Now, let's move on to the next problem. Here's problem 4. A ship is traveling along the equator. How fast must it travel so that the sun appears stationary to the passengers? Which direction should it travel in? The Earth's radius is 6,400 kilometers. Let's start with a quick sketch. It shows the Earth revolving around the sun. As the Earth spins, its angle to the sun changes, making the sun appear to move. For the sun to appear still, the ship must travel against the rotation of the Earth. Let's list givens and finds. The problem gives us the ship's distance to the center of the Earth, 6,400 kilometers. So we know the radius of the ship's circular path. We also know the time the Earth takes to spin around its axis, 24 hours. In addition, we know that ship passengers don't see the sun move. That means that the ship must be moving against the Earth's spin. The ship's angular velocity must equal the Earth's angular velocity, but in the opposite direction. They have the same speed, but different directions. Since the Earth and the ship have the same angular speed, they take the same amount of time to complete a revolution. That means that they have the same period, t. Here's some extra proof. As this formula shows, an object's period is determined by its angular speed. So any two objects with the same angular speed must have the same period. The problem wants us to find what speed the ship must travel at to counteract the Earth's rotation. Since the problem didn't say angular speed, we'll assume it wants the tangential speed. Let's pick which formulas to use. These are the formulas we can use to find tangential speed. Since we don't know the angular position at two different times, the second formula won't help us. We'll have to use the first one. It says that the tangential speed equals the circumference of the circular path divided by the period of the object traveling around it. So tangential speed equals 2 pi r over t. We already know the radius of the ship's circular path, and we also know the period of the ship's rotation. Let's apply the formula. When we plug in r and t, we get a tangential speed of 1675.5 kilometers an hour. What about the direction of travel? We know the ship travels in the opposite direction of the Earth. When I first drew the sketch, you saw that the Earth spins to the east, which makes the sun first become visible in the eastern part of the sky. Since the ship is trying to travel in the opposite direction, it must be traveling to the west. Here's another way to think about this. Normally, the sun moves east to west relative to the passengers. If the passengers are also moving east to west, the sun will appear stationary. So the ship must also travel east to west, or westward. Let's move on to the next problem. Here's problem 5. 2 cities lie along the equator. To get from one to the other, a ship must travel 3,045 kilometers along the Earth's surface. If it takes the ship 1 day to make the trip, what is its angular velocity compared to the surface of the Earth? The Earth's radius is in 6,400 kilometers. Here's a quick 3D sketch of Earth. Here's the equator, and here are the 2 cities on it. I'm going to redraw the overhead view of the cities sitting along the equator. S marks the curve between the 2 cities. Let's list the givens and finds. They give us the distance along the curve between the 2 cities. That's the arc length, S. They also give us the time it takes to travel from one city to the other. We know the radius of the Earth as well. We want to find angular velocity. Let's figure out what formulas to use. To find angular velocity, we can use these. We can't use the first one because we don't have the theta versus time curve. The second one also isn't convenient because we don't have the ship's period t, the time it takes to travel all the way around the Earth. But we do have the time the ship takes to travel between 2 positions, delta t. Since we have delta time, the third formula is a good choice. But we still need to know the angle between the 2 cities. Time to pick another formula to help. Since we have the arc length s, let's look at the arc length formulas. We want to find the difference between 2 angular positions, so the second formula is a great choice. We can rearrange it and solve for the angle between 2 points. Let's apply it. When we rearrange, we get that the angle between the 2 cities equals s over r. We know the radius and we know the arc length. When we solve, we get 0.48 radians. Now we can plug that into our expression for the angular velocity, which gives us 0.02 radians per hour. We're almost done. The problem asks for the answer in revolutions per hour, so we need to convert radians to revolutions. 1 revolution equals 2 pi radians. And since we want revolutions per hour, revolutions needs to be on the numerator. So we multiply by 1 revolution over 2 pi radians. That gives an angular velocity of 0.0032 revolutions per hour. Let's move on to the next problem. Here's problem 6. A particle is traveling around a circle. The graph below shows its angular velocity versus time. In part A, we want to know what the final angular position is at 5 seconds. Let's list the given and finds. The problem gives us the omega versus time graph and the initial position. It wants us to find the final angular position. Let's figure out what formulas to use. In this case, only one formula gives us the final angular position. Here it is. It says that the final angle equals the initial angle plus the area under the omega versus time curve, from the initial time to the final time. We have the initial angle, and we have the curve. Let's apply this formula. We find area under the curve by taking the area above the horizontal axis and subtracting the area below it. These areas are just rectangles, because the angular velocity, omega, is constant for uniform motion. So we have 2 rectangles, and their area equals the height, omega, times the width, delta time. When we take the initial position and add the area under the curve, we get 0.6 radians as the final angular position. Onward to part B. What is the total rotation during the first 5 seconds? Time to pick a formula. Once again, we only have one formula to choose from. It says that the total rotation equals all the area between the omega versus time graph and its horizontal axis. That means you take the area above the axis and add the area below it. Let's apply it. Again, these areas are just rectangles. The height is omega, and the width is the difference between their initial and final times. We take the absolute value of them, which forces us to treat all areas as positive values. Once we add, we get the total area under the curve. When we plug in our values and simplify, we get 5.4 radians. Let's finish this problem off with part C. Draw the angular position versus time graph. Let's figure out which formulas to use. In this case, only one formula gives us the angular position at some time after the initial time. Here it is. It says that the final theta equals the initial theta plus the area under the omega versus time curve from the initial time to the final time. But if we want to draw the entire graph of the theta versus time curve, we need to find theta at every time during the time span we look at. Luckily, we can get away with finding the final theta just at the initial time, any time where omega changes, and the final time. Then, we just connect the dots. Let's do it. We know the initial position, so we just need the area under the curve. At t equals 0 seconds, the area under the curve is 0. At t equals 2 seconds, the area under the curve is the area of the rectangle on the left, 1.5 times 2. At t equals 5 seconds, the area under the curve is the area of the left rectangle minus the area of the right rectangle, since the right rectangle is below the horizontal axis. Now that we have the areas for these 3 times, we know the final angles of these 3 times, 0, 3, and 0.6. Let's plot those points. When we connect the dots, we have our graph of theta versus time. Nice work! In the last video, we learned all the concepts and formulas. We just finished practicing our skills, so we have nothing to fear about uniform circular motion. Well done! If you liked the video, you can thank me by giving me some quick feedback on the video to help me improve. Just click the link in the description to fill out a quick 1-minute Google survey. If you found this video helpful, subscribe to get notified when I release new content. As always, keep at it and crush the course.